G'day everyone. This is Richard Walding here. I'm just going to run through a PowerPoint slide that I showed at the Griffith Cutting Edge STEM conference last year down the Gold Coast and in Brisbane, but also at the UQ STAQ conferences a couple of weeks before that. These were both done in November 2019. So on the screen you can see the PowerPoint slide for the first conference. So that was at UQ. Now, at the time, I didn't do a voiceover for these. I just presented them live, but now people have asked for a voiceover just to see, just to remind everyone of what was happening. So the next slide just shows the cutting edge one down at Griffith at the Gold Coast, and then I did a third one at Griffith at Nathan. So here we go. So look, that's just a part of my web page. The only reason I've got that there is if you forget where you've seen this video and you want to find the link to it, it'll be just a YouTube video. You just go to my homepage there at the top of the screen and you'll see a couple of links down the bottom, UQ, STAQ PowerPoint and the STEM PowerPoint. Well, they're both the same. I'll combine those. Okay, now in the physics syllabus, senior physics syllabus, there are 4 pracs to do with electromagnetism. You can see them there. The first 2 are the mandatory ones, strength of a magnet at various distances, and the second one, force on a current carrying wire and magnetic field. Now, I've numbered them 7.1 and 7.2 in the text, but they're just in section 7 really of, well, they're not in any section in the syllabus. They're just under electromagnetism. But that's chapter 7 for me from the Oxford text, and then chapter 8 for the next 2, which are the suggested pracs, the induction one, and then the last one is the transformer prac. I won't spend too much time on those because they're not such a big deal. Okay, so here's the first prac that's mentioned in the syllabus. Now that diagram comes straight out of the QCAA data test, the sample data test. You probably all have seen that. They gave some data and then you had to analyse the data. Now it's pretty much the way the setup would happen. You'll just see the 2 bar magnets there, permanent magnets. In this case they've got the like poles, the north poles together, separated by distance r, and then they're on a scale. You get a scale reading. They're on electronic balance of some sort. Now they've got it reading in newtons, but most students would do that typically in grams. Now it does work pretty well. I'll just show you the setup I used. Now your setups will be a lot different, but this is just one just as a demo. But what you'll notice is I've got the north and south poles here. I've got unlike poles together. So that top magnet will attract the bottom one. So the scale reading, as you bring them closer, the scale reading will get less and less. Now if you start off with it zeroed or tiered, what you'll find is that it goes into the negative. But it wouldn't matter if it was 2 like poles together. You get the same scale readings. Now I wouldn't call them, students often call them the mass in grams. Well, it's not really the mass, it's just a scale reading in grams. And what I've done here, what the student's going to do is just adjust the top magnet. You can see a ruler behind there. Now, it looks like there's a bit of parallax error, but when you get down level with it, that's right on the 0 mark. And then as she winds the lab jack down, the distance gets smaller and you get a bigger negative reading on the balance. Okay. I should mention, if you're using vernier calipers to measure the distance, and maybe not for the first prac, but when you do the student experiment, you might like to use vernier calipers to get a more accurate reading. Make sure you get the plastic ones or the fiberglass ones. These are from JCar, they're about $13. I started off with steel verniers, and of course after one try with them, they just stuck to the magnets and it didn't work. So make sure you get the plastic ones. You can buy plastic ones for about $4 or $5 each. Even super cheap autos sometimes have them, but you can see them on the line online. Anyway, so here we go. This is a short video. I'll just show you what happens. So the student will wind the lab jack down, and you can see it's getting closer, and the reading on the balance is getting greater, so it's up to 3, 4, 5 and so on. Okay, and I'll stop there. You get the idea. Okay, now the next slide, this is the results of it. What you'll see, I've got the distance along the bottom in meters. Now you could do that in centimeters, it wouldn't matter, but it's 1 centimeter, 10 centimeters up to 50 centimeters. So you start far away. No, that's 5 centimeters. What am I saying? 5 centimeters, 4, 3, 2 and 1 centimeter. And of course, when we're down to the 1 centimeter, the force, which is the scale reading converted to kilograms and then multiplied by 9.8 to get a weight or a force reading, is there. Now, if you get Excel to give you an equation for the line, you'll see you have to choose a power relationship from Excel. And this one here gives me a negative 2.0. So effectively it's x raised to the power of negative 2, which is inverse squared. So you'd be tempted to say that's an inverse square relationship. And what students would do for the first experiment is just say it's inverse squared. They'll say to you, what should it be? And you know, that's where you have to decide what to tell them. And I'll give you some information in a minute about what you can tell them. But it's good enough to say that's the relationship. They can linearize that. And this is actual real data from I took it from some of my students who did it. And you'll notice this particular group got 1.84. So it's almost inverse squared. And I've got down the bottom here, what students say, what should it be? Because everyone wants to know that. Okay, when we linearized it, so we plotted the inverse square, we plotted 1 on r squared at the bottom, and up the y-axis, the force in newtons, or the weight, the scale reading basically, converted to a force, and you'll see it's a beautiful straight line, looks pretty straight. There's a bit of a curve in it. Okay, not much down here, there's a little bit of a curve. But look at the r squared, 0.99, so effectively 99% of the data is accounted for by the straight line. Well, you can think of it that way. And there's a small y-intercept there, and you could talk to the students about what that means. Okay, let's move on. Now, if you wanted to, you can do a log-log graph of this. Now, the slope of a log-log graph will give you the exponent in the relationship, and you can see it's negative 1.8 here, negative 1.84, which is what Excel said, but this is just another way of getting to it. If you're not sure what it is, you can always plot log-log, and that'll give you a good starting point if you want to linearize. Okay, now some modifications. For the student experiment, there's a number of modifications that are available or that students could make, and let's just run through some, because they'll need to choose, a refinement or an extension or whatever, and you want to be able to give them some ideas. So you don't want to get, this is what I've said here, you don't want students to get the idea they can extrapolate the findings beyond the parameters of the inquiry. So they might have got inverse square for the relationship, but is that true when it's a greater distance than 10 centimeters or shorter magnets? Now, I've used magnets that are about 8 centimeters long. What happens if you use the little button magnets, or if you use really long magnets, or if you do it, instead of 5 centimeters, do it at a meter? What's the relationship? Or 0.1 of a millimeter? Who knows? You could do anything like that. Okay, so I've said here the parameters set the limitations. Now, when they're discussing this in their student experiment, one of the big areas is to discuss limitations, and there's, you can get up to 5 and 6 marks just for doing this really well in the discussion section. So it's good to concentrate on what are the limitations and how you overcome them. So let's have a look at some of these are the 3 possible modifications. Now the first one, the simplest one, is the refining one. Now you'd refine an experiment because you thought the original wasn't accurate or precise enough. Now that previous experiment was quite precise. You know, if you did it a couple of times, you find the error bars are quite small, but you don't know how accurate it is because you don't know what you're comparing it to. You don't know what the accepted value is. So you could say it wasn't accurate or precise, but you could also say you want to make it more accurate, or you want to make it more precise, whatever you're trying to do. More precise, probably. So here's a couple of ways you can do it. You can make modifications to the way the independent variable is changed. Now the independent variable is the distance apart. So you could do more trials. So instead of doing the one trial like I did, you could do 3 trials. Or you could refine it by changing the way the dependent variable, that's the force, is measured. So you could have a different measuring device, different type of scale balance or whatever you wanted to have. And then the conditions, you know, often you get, there might be a changing magnetic field or something's going on in the room that affects the readings on the balance. For instance, often with air conditioners, some groups will find the air is blowing on them when the air conditioners come on or the fans come on, and it doesn't happen other times during the experiment. So you want to, you know, fix up the precision. In either case, or any of those cases, you have the same independent and same dependent variables. I've got there same IV, same dV. Now another thing you can do is to extend the experiment. Now I've done it, you saw me do that one over 1 to 5 centimeters, I think it was, but you can't generalize past that. The data didn't extend beyond that range of parameters, so you've got a problem generalizing. So one of the things you could do is to go outside of that range. Okay, it was linear when it was linearized. It gave a linear relationship when it was linearized, so that tends to indicate it's 1 on r squared. But can you generalize outside of or bigger than the 5 centimeters? You know, it could be 1 on r cubed, or 1 on r to the 4th, or 1 on r, just 1 on r, who knows? So they're the things you can do. You could just change that separation distance to different values. So in that case, I've written there, you've got the same IV and the same dV again, but you've just gone outside the range. Whereas in the first one, you've tried to just fix up the precision in the range that you're in, and to see what happens. The third one is the redirect. Now there could be some factor that's affecting the relationship, and you want to investigate that factor itself. So it could be temperature. I've said there it could be temperature, the length of a magnet. Now that's a big one, on the magnetic field strength, or even the strength of a magnet. Maybe this relationship holds for weak permanent magnets, but does it hold for strong permanent magnets or electromagnets? And that's a good one. Electromagnets are something really worth considering. So in that third one, the redirect, you'll notice I've written at the bottom, you've got a different independent variable or dependent variable, so you could change either of those two. Probably best not to change too many things, just change one, and maybe do maybe include a refinement in there as well. So collect more data, more trials I should say. Well, it's actually doing triplicates rather than increasing the number of trials, but doing triplicates or have more trials, or in the last case, the redirect, use a solenoid or something like that. Okay, let's move on. Now, look, what I've done here is I've had a look at different sections within that little bit of data that I collected, and I did this again, for the purposes of this talk. So I made sure I got data all collected at the same time, and with the same setup. I wasn't just using different things every time. So you can see there, I've got it listed, the independent variable in centimeters at the bottom, just to make it easier to talk about. You'll notice I've gone from about 0.3 of a centimetre. Okay, so that's about 3 millimetres, all the way up to 2 centimetres. Up here you can see 2 centimetres. So usually I start with it further away, the greatest distance, and then bring the magnets closer together and the force gets greater. Now the reason I've used unlike poles is it attracts the magnet up, so the scale reading gets less, or actually the scale reading goes bigger in the negative direction. If you use like poles as the data test, the sample data test from QCAA has, you get a repulsion and one of the magnets just falls over. It pushes it away. Now teachers have said to me what they do is they make a little holder for the magnet on the balance, and something as simple as a specimen jar with a hole cut in the lid and the magnet poked through it. Now I tend to use that, and you just put a couple of brass weights in there because when you're getting really close, it tends to really lift the magnet off the pan. So you need a couple of heavy weights in there, 100 grams or something, just to stop anything from lifting up off the balance. Okay, so you'll notice there it looks like it's a x to the negative 1.8, not quite inverse squared, but certainly not just inverse, but somewhere in between, closer to inverse squared. Now that's going from 3 millimetres up to 2 centimetres. Okay, so let's have another look. Now if we go from 2 centimetres up to 5 centimetres, what you'll notice is what Excel does is deduce a formula for that, and they get a negative 3.2. So you'll notice it's a difference. So it's 1.8 when it's in close, and then 3.2. Now you're probably wondering what happens from 5 to 10 centimetres. So let's have a look. Oh, wait a minute, we're going to do this first. Look, this is at the stage where the students say, well, what should it be? So what we need to do is work out in theory what it should be, and then I'll look at it further on. So here's two magnets. I've got the like poles together as the data test had. Now this is not the easiest way for the prac, but for theory it makes it simple. Okay, so what you can do is treat that as two charged objects, like and use Coulomb's law. So here are some of the parameters you've got. You've got now the R distance is the separation distance between the two magnets, and then you've got the length of each magnet. Now I had about 8 centimetres for the length for both of them, and the R distance I went from about 5 centimetres down to 0.3 of a centimetre. Now what you can do is look at the forces, just apply Coulomb's law in different ways. Now what you've got is these two north poles are repelling, but you've also got an attraction between this south pole here and that north pole there. So that's an attractive force. So you've got a repulsive force between these two, and they're close together. Then you've got an attractive force between that south and that north, but then you've also got an attractive force between this south and that north. Now the opposite poles will just double that because they're the same, they'll be the same sort of dimensions. So having a look at Newton's Coulomb's law, when you've got north and north together, the force between them is, well, it's not equal to, but it's proportional to 1 on r squared. That's just Coulomb's law. If you've got a north plus south, now you've got the force is the distance here, which is r plus L. So you've got the distance apart is r plus L. So that south to that north is r plus L away. Okay, so you've got two lots of that. So it's twice that because you've got a south and a north and a south and a north. Lastly, you've got the outside souths repelling. So they're like poles. So the force between that is proportional to 1 on, now the distance between the two south poles is L plus R plus L. So here it is here, R plus 2L, and that's all squared because it's Coulomb's law is inverse squared. So you stick all that together and you get the total force is the sum of those three. Okay, now I know it's only proportional, but we'll just treat it as being equal. It's equal to some constant times all of that. Now if you set L to 10 centimetres rather than, I mean my magnets were 8, but let's say you've got 10 centimetres to keep this simple. And then we plot this relationship for F versus R, and you've just got a 10 in there and a 10 in there times 2. So you can see the total will be the sum of all of that. Now, if you do that, look what happens as you go from 4 centimetres here up to, say, 30 centimetres. It turns out that the relationship is it's not inverse squared, it's not inverse cubed, it's somewhere in between. So in theory, it's somewhere between inverse squared and inverse cubed, between 5 or 4 centimetres and 30. Now you could say, what about, you know, shorter than that or longer than that? Well, let's have a look. Let's have a look right down here where it's 0.4 of a centimetre all the way up to 30 centimetres. So the previous one, I started here at 4 centimetres. Let's now include all this in from 0.4, okay? And on average, if you like, the relationship is nearly inverse squared. Okay, so what else can we do? You can look at all aspects of this and to see how it changes as the R distance changes. So look, here it is from 0.4 of a centimetre up to 1, basically from 0 to 1 centimetre. Here it is from 1 to 5 centimetres. Okay, so you'll notice it starts off at inverse squared. And it's a little bit more than inverse squared here. It's 2.1, so it's 1 on x to the power of 2.1. What about 5 centimetres up? Look, 5 to 10, we're up to 2.42. It's something about halfway between inverse squared and and inverse cubed. Okay, when we're up to 10 to 20 centimetres, it's almost inverse cubed. And 20 to 50, it's a little bit more than inverse cubed. Okay, and what about 50 onwards? Now this is in theory, if you remember. Look, it's up to 3.5. Now you could say, well, what about beyond 100? Well, eventually it gets up to inverse quad, or whatever you might call that, quadruple, -4. So 1 on x to the power of 4. So when the student says, what should it be? Well, you can say, well, it depends on how far away you are and how big the magnets are, and you know, a lot of other factors come into it. But that's the logic behind all of that. Now, that's a simple bit of logic on that formula I use with Coulomb's law. But scientists have done a lot of work on this, trying to investigate the real relationship. My work is on anti-submarine detection, and how do they detect a submarine, which is basically a floating magnet. How do they detect it with a galvanometer? And you know, what's the relationship between a sub and the depth the submarine is in the water? Well, scientists have spent time since actually about 1890 in England. That's when they first started investigating that relationship for submarines. Now, look, if we look at the theory, before I look at the theoretical paper, let's have a look at that relationship. You can see along the bottom, as I increase the range, the relationship changes. So it's inverse squared down here, somewhere around about there, and then inverse cubed around about 20 to 50 centimetres, somewhere in there, and then it gets up to a higher value. So depending on where your students' experiments are, they'll get different values. And it's not so much that they have to work out the accuracy. Really all they're doing is working out the relationship and commenting on the relationship. And really they should be saying, well, there's various laws of nature. There's Newton's law of gravitation, which is inverse squared. There's Coulomb's law, which is on electric charges. That's inverse squared as well. So perhaps magnetism is a part of this law of nature, and it should be inverse squared. but other factors come into it. Okay, I'll just show you, this is the physics paper, part of it I was telling you about, from the European Journal of Physics. Now, they've done these quadruple integrations here, but basically they're using different size magnets, and they're looking at the R distance from all aspects of the magnet, not just the perpendicular one, but all aspects of it. Then they've got the thickness of each magnet, H here, the distance apart, the distance between centers, and it goes on, radius of each magnet. Now, you wouldn't even have to show students that, but I'm just showing you that it's not as easy as you might think. Anyway, now another way to change the way the DV is measured is to set up this. Now, I set this up in my classroom, and a couple of girls, or my students, did it for actually back in the other syllabus, which was the extended experimental investigation. You can see the girl Leanna did it here in 2019. But all she was doing was had two magnets with like poles together, so say two north poles on a ramp, and measured the distance between that using a vernier caliper, and then she raised the ramp. Now, as you raise the ramp, of course, the theta increases, so sine theta increases, and you get a greater force down the incline. So then you can plot R versus the force, because you'll have the angle. Now you can measure the angle with a protractor, or in this case, we had a 1 meter piece of laminated wood from Bunnings, a couple of dollars, and she just measured the height, so she could work out the sine theta based on the height and the length of the incline. Now look, I should mention something here while it's up. And what you'll notice is that I've got the vectors here. So there's the weight of this trolley going straight down, so it's vertical towards Earth, so that's Fg. Now I've resolved that into the two components, the one Fp, if you like, the parallel component, which is equal to Fg sine theta. The other component is the perpendicular component, so which is Fg cos theta. Now what you'll notice, I've left the three here together. Now I say to the students, well, you can't really put the three together. You're resolving that big one, the Fg, into the other two. So the Fg goes, you should cross it out because it's now replaced by those two. And students say, yeah, that's all right, we understand that. But they just leave it in their exam papers, and that's fine. Because it's not exactly what they're asked. They're asked questions about the components, not the vectors, the diagram of the vectors itself. But if you remember back to the external exam for 2020, the first multiple choice question had something like this on it. And in one case, they had the three vectors there, which would have been wrong, because you have to get rid of the perpendicular, the vertical one here, the Fg, because it's replaced by the other two. So it's a simple point, but for the purposes of being correct, and the EA asked that question, so just be careful. Okay, so when she plotted that, here's the problems. Once you get a big angle, the cart tends to fall off to the side. You need some way of keeping it in place, or just not use such a big angle. Keeping them in line, now only has to be a centimetre off to the side, and the R distance really is, you're getting errors. So there's her relationship, the distance apart and the force, which is the Fg sine theta, there. Now she needed to know the mass of the trolley. I'll just go back one. She would have weighed or got the mass of this trolley to calculate the Fg, which is just mg. Now what you'll notice is she's got an inverse cubed relationship for that, and lovely R² value, so that looked pretty good. Now that was a simple one to do. She I remember her doing error bars, and she said you can't even see the error bars, they're so small. So that's pretty neat, and that's why it's probably, it's just a good little prac if you want to do it. It's quite simple. Students can easily see what they're doing. Now another one, another student in the class thought of doing it a different way. What she was going to do was change the mass and keep the angle constant. So she left the angle at, say, 30 degrees. She added brass masses to the trolley, so the FG component, the FG part got bigger, and as that got bigger, the R value got smaller. Okay, and again, now this is my diagram, not hers. I should have removed the FG, but it's a good talking point to leave the 3 there and talk about that. Okay, now here's hers, and again, she got inverse cubed for that, distance along the bottom and force up the side. So a lovely prac you could do for your student experiment. Simple, they can understand what they're doing. You get reasonable results, you get them in a good time, fits in well with theory, and so on. So a nice little modification. Now something else you could do, if you want to do this whole prac in 10 minutes, when you could have a student who's away and you want to quickly get some data, and if they work this out themselves, you can give them a few suggestions. It's easy to collect data. Now all I've got here, now I took this to the conference itself and I was holding it and waving it around. Just got 2 magnets. I think they're 20 centimetre magnets, I'm not sure, by about 1 centimetre. They're about, I think they're quite expensive, but you can get them from Bunnings, but I think they're about $20, maybe $15 each. But from Bunnings you can buy packs, but they don't have to be that size. Well, look, I've just put a 1 in the bottom of a measuring cylinder, and I've written on it S for the South Pole up, and of course I've got this one floating in mid-air, if you like, with the South Pole on the underside. They're repelling. So I know the mass of that magnet, so I know the force between the two. It's just mg, and I've got a reading here. You can see it's around about just over 6 centimeters. Now what you want to do is increase the mass of the top one and see what happens. So what I did, I added just some brass. Actually, these are from the projectile experiment, and it squashed them down. Now I wouldn't do this, but it was just a demo I was using, because what happens is these balls tend to jam themselves in there, and they don't work very well. You get too much friction and you don't get reliable results. So a better way is to, if you think about it, what could I do? And all we did was get rid of these brass masses, and I just put a piece of dowel, a piece of wood in there, and then on the top just put 50-gram brass masses on the top, and that worked like a charm. They go down. The problem you've got is getting it all out, because as you turn it over to slide it out, the bottom magnet attracts to the top magnet, and they end up smashing the glass. Oh, that's what happened to me, but you'll work something out. Okay, so that's the relationship. Now look, I've got the mass on the bottom and the distance up the side. So this would be the first stage of just plotting your data. You're not doing an R versus F graph or force versus distance graph. This is distance versus effectively the mass. And so you're getting a relationship here which is up, the inverse of what it would be if it was F versus R. So that's 0.22. So it's about inverse 1 on to the power of 4, x to the power of 1 on x to the 4th, roughly, or a bit more than that. Not very good data. Look, it's a bit wobbly through there, but it's a simple one to investigate, and you get lots of interesting data. Have a big error, but I only did one trial. Sorry, I did 1, 2, 3, 4, 8 trials, but I only did one test for each trial, if you like. I'm just being careful about the words trial and tests. The trial, one trial is where you change one of the variables. A test is like a duplicate or triplicate. I don't know, it's a better word for it than test, but that's what I can use. But people generally call them, you do 3 trials at that mass, another 3 trials. Really, it's 3 tests at that trial, but anyway. And that's how the syllabus defines it, like I'm saying. Okay, another thing you could try, and this goes back probably 200 years or so, they used to do this sort of experiment, but basically you just bring up a magnet to a compass. Now I've got the compass aligned north-south, and then I slowly bring in a compass, and then there's a torque on the compass needle which brings it, because that's a north pole. As I bring that closer, it should push it away. But it depends on whether you use a north pole or a south pole, for what you get. So let's have a look. Now, this doesn't make sense. If the top's a north pole, it shouldn't attract it. I was doing the demo at the conference, and I thought, what the hell's happened here? How can that be a north pole of a magnet? And this is the north pole, and they're attracting. Till I realized, I tried this magnet out, and it's actually, the poles had been reversed. Unless you're careful at school, you throw all the magnets together in a box, and some of them tend to get their polarities reversed for some reason, so obvious reason. So I tried it again, and that made more sense. So I got another magnet at the conference and showed it being attraction. So when that magnet was not there, this needle pointed directly north, and as I brought that up, it applied a force to the needle. There's a torque on that, and it got bigger and bigger number of degrees the closer I brought it. Okay, you can see here I'm up to, that's at 16 centimeters. That's about 45, 47 degrees. Here it's, what's that, about 75 degrees or something, and we're down to 10 centimeters. Okay, so now the logic is this. The magnet applies the, I'll start again. The Earth's magnetic field, the horizontal component of the Earth's magnetic field, which is FH, points in that direction. Now you can get that out of a book for the local area, or you can look it up, what the FH value is for your town. And for where I did it, which is Brisbane, I can look it up, and it's actually measured in nano Tesla. Oh, sorry, no, that'd be the B value. This is just the force. So there is a horizontal force being applied to that by the Earth's magnetic field, and what you're measuring is theta, because it pulls the needle around, and the resultant force is that direction there. So the magnet must be applying a force to the magnet, to the compass, equal to this line here. So the combination of the force due to the Earth's magnetic field and the force due to the magnet produces this, what would you call it, the resultant force at an angle theta. So the force on the magnet is just force horizontal times tan theta. So you can plot, you can actually work out what the force of the magnet is using that relationship and treating FH as a constant, and work it out and draw it with the distance r along the x-axis. So what we got was this, and you can see here's the radial distance. I started off at 35 centimeters, brought it in. Now you can, I took a data point at 16 centimeters, you saw, and then another one at 10, I think it was. Get that. Now that's almost inverse cubed, negative 2.89. So that's a lovely little prac you could do, pretty simple. Kids understand it. They mightn't understand that vector diagram, but you could explain that to them. Okay. I just linearized that, and you'll notice there's a little bit of a curve in there. So it's not quite inverse cubed. The R value is not too bad, pretty good. And, you know, I think if you tried 1 on R to the 2.8, you'd probably find it's more linear, and that would maybe get up to 0.99. But that's for the students to investigate. Now look, another way you can extend it, if you remember what I said earlier, was that you can change the independent variable. In this case here, I'm changing the strength of the magnet, or strength of the magnetic field. Okay, so I'm changing the force that will be applied to a little block of steel here. Now that's just a cube, 1.5 centimeter cube from the old IEC metals kits. But you can use anything there. You can just get a big steel nut from Bunnings or whatever you like. So I kept the distance the same. Oh, I've set out various distances. So you can change the distances, or you can change the current. Now, if you change the current, you know the formula is B equals mu Ni, where N is the number of turns per meter for the solenoid, I is the current. So I've got a reading here for the current. Look, it's 2.98. I've got a scale reading here, which will be a force. Now that's negative 0.57 grams, it looks like. Yeah, 0.57 grams. And just change the distance, but keep the magnetic field strength the same. Alternatively, change the current and keep the distance the same. Here's one where I kept the current the same. This is actually a student's. You see a name here, Willow Wilkes. That was the year before. Now this was an EEI back in the old extended experimental investigations days. So what she did was use an ammeter and just changed, I think she just kept that constant and then changed the distance, and she had a ruler. Look, I think the next slide shows that. Yeah, here's the setup. So there's the solenoid. She had a piece of steel in the middle. That was just an old bolt, just to tend to concentrate the flux a bit. The ammeter, so she could work out, or she could keep the value constant. Yeah, that is an ammeter. It's going out of the positive through the solenoid, out of the solenoid into the ammeter. That's in the 10 amp connector, out of there through the negative, and then back to the power supply. Now look, I've used it's just the half-wave rectified power supply, but it's fairly linear. If you put that on the oscilloscope, you'll see it's linear, even though it shows like a half wave that's been rectified, and it looks like a series of M's. It actually is quite linear. There's a big capacitor in there, and when you've got a reasonable resistance, now, you know, it tends to be pretty flat with no ripple. If I was doing it again, I'd use these two terminals down here. If you got that, that's filtered and rectified, and it's lovely and flat. But it depends on what you've got in the lab. This is about, I think it's about 8 ohms for these solenoids. Now I think they're just the IEC air cord solenoids. They're about $80. I think they're about 700 turns, and I think they're about 15 centimeters long. But anyway, so she's using a magnetometer here. Now she would have brought that over onto the ruler, read off the distance, and that's just a magnetometer from Vernier, and it's plugged into a lab quest, and which is reading magnetic field strength. And here's her data. Her data is the blue dots. Now she's trying to work out what it should be theoretically using, that's actually from a Bio-Savart law. She's tried her own integration. Now this is a girl who was doing well in her Math C, I think it was at the time, and she sort of understood what she was doing. And she ended up really pleased with herself that the experimental data, the blue dots, ended up being fairly much the same as the theoretical data for her, for the way she developed the formula. Okay, let's move on. Now, another experiment, the other mandatory experiment is to investigate the force acting on a conductor in a magnetic field. Now, when you think of conductor, you usually think of a wire, a current carrying wire, and the magnetic field produced by permanent magnets, and that's the simplest one. Now look, I've got a diagram here that comes from the mock external exam. That was for school use only, so that wasn't publicly available at the time, and the sample data test that you would have probably all have seen, but it's this figure here. Now, okay, so there's the horseshoe magnet. Now this is a stylized diagram. I remember talking to QCAA about it and saying you'd never get a reading on a balance with a magnet this far apart and the wires just sitting there, not clamped on and so on. And they said it's just a stylized diagram, so that's fair enough. But basically, you've got there's the conventional current going through the wire, and you've got a magnetic field going from north to south. Now, if you use your hand rules, now I teach the Fleming's left-hand rule for forces, but some of you will use the right-hand palm rule or slap rule, which is what I used to use at one stage, but Oxford prefers the Fleming's left-hand and right-hand rules. So I've done all of the text, and my students learn it in terms of Fleming's left-hand rule. And you can show that there's a force on the wire. Now it depends on the way you've got the current, but the force can either be down on the wire, pulling down on the wire, which in other words will pull the magnet up and you'll get a negative reading, or you can reverse that and have a force pushing up on the wire, which will push the magnet down. Now, there was some trouble in the mock EA, I believe. We had to get that corrected because the answer was back to front. It's a tricky one, and you want to make sure students can sort that out. Okay, so now here's the thing I developed, and I showed this at the conference last year. Look, all it is, you can see it here, is a little bit of aluminium channel from Bunnings. Now that's about $6 for a metre of that, and that's about a centimetre by a centimetre by a centimetre. And I've just got a cork, wine cork with a bit of wire through it, stiff copper wire, and I've got two little button magnets. Now they hold each other in place because there's a force of attraction between opposite sides. You see I've got a south side on here, so the inside must be north. So I would have had an inside on the other one as a south pole and then a north pole at the back. So they attract each other. So you've got a strong magnetic field going across. So it'll be going from this side across to the other side. And you've got a current coming through here at right angles. And that's about it. Now, I've assumed that the length of wire in the magnetic field is the same as the diameter of the magnets. Now, they're a centimetre across, I believe. So I've assumed the wire in the magnetic field is a centimetre. But you know very well that the magnetic field also comes around the outsides a bit, gradually gets weaker and weaker. So I think some students have said to me, well actually, and teachers have said, you'd be better off making the piece of wire itself less than the diameter of the magnet. So make the piece of wire maybe a half a centimetre and put it in the middle. Trouble is you're looking for reasonable sort of readings on your balance. And if you're using balances that give a scale reading to 0.01 of a gram, you know, you've got to have a reasonable sort of current or length of wire in the field or magnetic field strength from the magnets. But if you want to go up to your chem lab and grab some of their 3 decimal place balances, which are about $2,000 each, they might let you have them. You can do it that way. Okay, I wouldn't try putting magnets side by side because they won't sit there if you think about it. They all flip around and stick to each other. So you just need a biggish magnet. Now you can buy them, you know, 25 millimeters across. Should do the trick. Here's the setup. There's the 2 button magnets. You'll notice there's a chip off there. They chip very easily. My piece of aluminium channel and a cork, a bit of wire stuck in it. Now here's the setup. You can see I've got going through an ammeter into the well, I'll probably start over here from the positive. So it comes out of the positive. Conventional current goes into the solenoid, into the rheostat, and then through the wire, and then, or actually through a bit of wire, and then out of the rheostat into the one wire of the wire in the magnetic field, goes through the wire, and then back up and out here through the ammeter. I've got it hooked up here through the ammeter, and then out of the ammeter. Where'd that go? Back. I think I've got tangled up in there somewhere, but you can see it's just a complete circuit using the rheostat to change the current. Now, if you wanted to use this terminal down here of your filtered power supply, you've got good control over your current. But if you want a reasonable number of current readings, you probably need a little rheostat or a potentiometer like that, because you can only switch this from 2, 4, 6, 8, 10 volts. Anyway, I'll leave that to you. Look, here's a little video of it working. So she slides the slider, and you can see the current is increasing, and also the scale reading on the balance is increasing. So you just take your pairs of readings. Look, now I've gone in a bit closer just to have a look at the bits and pieces, and that's as I described before. Nothing too profound there. See, if I go back a slide, I think it's worth seeing. While that's happening, you could just video that, and then at leisure you can go and stop the video at various frames and take pairs of readings. Now, all you'd have to do is video it 3 times, and that's your experiment. You sit back and you can analyze, or you can get the pairs of readings at leisure, and that works well. They can do that at home then. Okay, I've shown that, and that was the close-up I've shown. And here's some of the data. Now, what you'll notice is here's the current in amps. There's the scale reading in grams, the second scale reading. So I've done duplicates here. Now, this was just for the purpose of the experiment, for the talk, getting some data. I've converted those to forces in newtons by dividing by 1,000 and multiplying by 9.8. Got the average force, and there's the uncertainty, which is just max minus min on 2, and that was that. So now if I plot that, current along the bottom, so that's the independent variable. Up the side is the dependent variable, and you can see I've plotted it. Now, I did it roughly just to get some big error bars, but when the students do it, or when you do it yourself properly, those error bars are quite tiny. In fact, students will say you can't even see the error bars under the data, under the marker, which is fine. But if you're trying to demonstrate some work with graphing and max and min gradients, it's a bit tricky. So I've done it purposely a bit rough so you can see this. Now look at the beautiful, the dots are, the averages are right on the line, or the line goes right through the dots, I should say. There's the relationship. It's nice and linear, as you'd expect. There's no y-intercept. It was pretty much 0. So if you extend that, it goes through to 0, which is nice. And students can say the force is proportional to the current, which is what you'd expect. And here's a little bit of graphical analysis. Now look, as I said, I made the error bars pretty big so that I could talk about it, but you can see here I've drawn the maximum value, the maximum gradient in orange, and the minimum gradient in green, and I've got the dotted line as the average, or the linear trend line. Okay, now you can do max minus min and all the rest of it, but here's the equations. You can see the maximum has a slightly higher gradient, 0.037. The minimum is slightly smaller. Now, we spend a lot of time on this in the Unit 1 and 2 work, but the alternative syllabus people will also use this in their, when they do work for the student experiment. But, you know, students for the student experiment could do this, but it's extremely unlikely you'd be asked to do some analysis of this in an external exam for the general syllabus. It just wouldn't be there, but it's certainly for the student experiment in Unit 3 you would. Okay, now look, I've just done some calculations here. The absolute uncertainty is there. I won't read all this out, but you can do a percentage uncertainty, and it's about plus or minus 13.6. Now really, when you do this, you get a percentage uncertainty of about 2%. So it's quite a precise experiment, but that gives, I've made it big so I can show you, but students would get a small value there, and they should be able to comment on the precision of the experiment based on the data like that. Now, just to analyze this, look, there's the gradient, and I've got the error as the sort of uncertainty associated with the gradient here. Now, one of the things we have to stress for students, and you know, I get the impression after marking some of the external exams with questions like this on it, they weren't understanding what the gradient was. They'd look at a graph and they wouldn't be able to interpret the gradient. So one of the things they have to be able to do is understand what the gradient means in terms of theory. So here's the equation, the relevant equation here, F equals BIL sine theta. Now sine theta is 1 because the it's at right angles to the wire is at right angles to the field. So you rearrange this and you have B equals F on I times L on the bottom. But when you think about it, F over I is the gradient. So if you go back to the previous graph, where is it here? F over I is the gradient. So you can replace the F over I in this equation by the word gradient. So B equals a gradient times 1 on L, which is the length of the wire in the field. Okay, now there's the gradient, 0.0033 from before, and the length of the wire is 10 millimeters, so it's 10 by 10 to the negative 3 meters. And that comes out to 0.33 Tesla, plus or minus 13.6%, and that works out to about 0.33 plus or minus 0.04 Tesla. In other words, a range for my magnet of 0.29 Tesla to 0.37 Tesla. Now, here's the catalogue item for this. Now, I got them from a company called Aussie Magnets, but Bunnings have them pretty cheap too, or there's a whole lot of suppliers. But if you run out and you want to get them quickly, just whip down to Bunnings if you can, or order them from somewhere. But Aussie Magnets were good, but you have to buy a pack. I think we had to buy 10 or something. No, 8, I think, in a pack. But the pull strength. Look, if you're ever interested in doing the pull strength of these magnets, what you need is well, in America, it's a 3-inch by 3-inch plate. That's 1/8 of an inch thick. So in metric terms, it's roughly, or you could just use 10 centimeters by 10 centimeter steel plate. That's maybe 5 millimeters thick. And then you hook a scale, spring balance up to it if you like, and just put this in a little plastic bag or tape a spring balance hook to it, and then see what force it takes to pull it away. And you get a reading of, well, I got you should get a reading of 2.8 kg. That's how they measure that. That's the standard method for it. Now, if you look, they're quoted as being 4,667 Gauss, which is about 0.47 Tesla. And I was getting about around about 0.3 Tesla. So it's in the same sort of order of magnitude, but a little bit out, possibly because of the magnetic field extending over the edge. It could be a whole lot of reasons. And let's move on. So let's assume 0.466 is the accepted value. I'm getting an absolute error of 0.14 Tesla by taking the the observed minus the accepted. And if you convert that to percentage error, it's about 30%. Now that's huge, but you can understand why it's huge. It's probably not a fair measurement of the field strength. But that's not what you were doing anyway. Your students were trying to look at the relationship. But if they're doing the student experiment, they might want to take it a bit further. So I've said there the summary a student might write is accepted value is not within the range of the uncertainty of the experimental value. So the experiment is not accurate. But I've said here that was never the point anyway. The main thing we're trying to get at is F is proportional to I, and I think we've established that pretty well. Okay. Now what you can do to extend the prac is, for the student experiment, they can run it backwards. So the first part of the experiment, you get data from zero, a current of 0 up to 1 amp, and a force which will go up to from 0. Of course, when there's no current, it should be 0, up to, whatever that happens to be in newtons, so many grams converted to newtons. Now what you can do is reverse the current. Right, I'll just leave the magnets in place, reverse the current by switching the two terminals around and continuing on, and you'll get readings in the opposite direction. So there'll be negative scale readings. If these were positive, these will be negative. Now that should go through the absolute, go through the origin, and you get a beautiful line like that. Now it should be linear all the way, and you can work out the percent error and all the rest of it. So that's a lovely little modification. It's so simple to do, and the kids will appreciate it because they will have done the first experiment. They just repeat that, do a few more trials to refine it, and then extend it by reversing the direction of current. Now they can conclude that the direction of the current has no effect on the relationship, and that's a lovely little conclusion to draw, and they've got all the data to back that up. So that's a beautiful little prac. Now look, another thing you can do to redirect, I said at the beginning, the syllabus talked about force on a conductor. Well, the conductor could be a beam of electrons, if you like. So now a lot of you will have this device. It's just a tube, evacuated tube, with a screen, a little metal aluminium screen coated in zinc sulfide. So when the cathode rays, if you like, the electrons come in through here, they go through that little slit, they're attracted to the positive, but the screen is at a bit of an angle, so the electron beam scoots along the surface. But if you bring up a magnet, it bends the ray down. I mean, that's the principle of the old TVs, the old cathode ray tube TVs. You could have a magnet in that direction. You could also have an up and down magnet. You could control the location of the beam both ways. Now, if you think about it, the stronger the magnet, or the closer the magnet, the greater the deflection of the beam. Now that's a part of there's questions like that on the external exam where you're comparing actually it's a mass spectrometer, which is the mass of the particle will also be affected, will also have an effect on the radius of curvature of this. So this particle effectively is undergoing centripetal acceleration down. So you can relate a centripetal motion formula to the force, the magnetic force that's being applied. But look, I wouldn't suggest this. It's just that one student or a group of students said that they wanted to do it because they loved watching the screen and me bringing a magnet up to it. Look, I just took a sample out of this girl's EEI at the time, and you can see as she makes the distance bigger from 4 centimeters to 20 centimeters, the amount of curvature gets less. So you can see a big curve here. Now she was trying to estimate what the radius of curvature was, and she did that, and she related centripetal motion formulas to magnetic field strength, and she had a neat little write-up for that. Got a nice conclusion. The results weren't very good. She didn't get what she would hope in terms of a linear relationship anyway, but anyway, it was a nice little prac. Now just a little bit more. Another thing you can do is to have the magnetic field produced by another current carrying wire. So you have two wires, the magnetic fields interact, and you can change the distance or you can change the strength of the magnetic field, and you get a different reading on your pan, on your electronic balance. Look, I used a 2 centimetre distance apart, and length of the rod. I had just a rod there with some loose wire attached. That was 10 centimetres across there, and just change the current. Now you'd need a voltmeter and ammeter in there. See what's going on. But that's a nice little prac. It used to be very common back in the earlier days when we had to, there was a formula, amperes formula for the force between two current carrying wires. We used to use that a lot, do that a lot. Okay. Look, just quickly on the suggested pracs. The first one is induction of electric current using a magnet and coil. So the introduction would be a magnet going in, you get a deflection. When it's not moving, you get no deflection, and then when it's coming back out, you get the reverse direction. And you look at what factors affect it. Now, the number of turns affect it, the velocity affects it, the strength of the magnetic field affects it, the distance apart affects it, and so on. Here's a neat little one you can actually do. All I did was had a glass tube through one of these induction coils. There's 1,200 turns. You can buy them from IEC, they're about $49. Drop the magnet through and you'll get a magnetic field being produced as it goes in, and nothing when it's in the middle, and then as it comes out you get the reverse field. So look, I did this. I was using one of these Handtech oscilloscopes, and we dropped it through, and there's the little the reading we got. Now you'll notice the what you can see about this. I hope you can see the time for it to go when it first generates an EMF is there, and then if you can see it, and then in the middle it's there, and then when it comes out it's there. Now you can see it takes longer to go in than it takes to come out because it's accelerating. So the magnet accelerates as it goes through, so it's going to be going at a lower velocity as it comes in than it comes out. So that's why that's a bit narrower there than across there. And you'll notice the peaks are different because it's going at a higher velocity here. You get a bigger EMF than up here. So that's a nice little experiment. Now I know guys at, I think it was BBC, were telling me they do that as a prac, and you can actually measure and confirm the EMFs with the velocity and so on. Here's the logic behind it. Look, it looks like a y is proportional to 1 on x graph. Right? You can see it's going to start down here and shoot up there like that. And look, it's x to the half, so that looks like square root. And so I've just done some logic over here. Y is proportional to root x, that's what it looks like. Or EMF is proportional to square root of the distance it's been dropped. Now, to derive that, we just use our vertical motion formulas. Now, I've put the y's in here, even though you wouldn't normally. It's just the students tend to, once they're in Unit 3, they tend to like the y's in there because the formula book has that y, whereas in Unit 2 it didn't. Okay, so that's 0, so you get rid of that. Vy squared is 2gsy, so V is equal to root s, or EMS. But so the EMF is proportional to the voltage, we know that, because of the formula E equals BLV, and we end up getting EMF is equal to BLV. Okay, that's what it should be, EMF equals BLV, and according to the formula we should get this inverse squared relation, this y is proportional to root x. So all that makes sense in theory, and it looks like it in practice. Look, if you plot EMF versus velocity, you see you get a straight line. Now here it says EMF is proportional velocity because in theory EMF is equal to B, the magnetic field. Well, I'm using a permanent magnet. L is the distance it travels through the field, and then V is the velocity. So it's a nice little one. Okay, let's move on. We're running out of time. Now, this is another way you can look at induction of electric current. All I've got here is just, I've used a micro ammeter, an analog one, because it's easier to see the deflections. If you use a digital one, there's a bit of a lag and it doesn't seem to make sense. Okay, so watch this. I've got a magnet on a rubber band coming into a coil, and you can see the deflections nicely. Okay, now if I repeat that, look, I'll just stop. Oh, it's going to stop itself. But what's happening is you've got a magnet starting at the top. It approaches the coil, stops, and then moves away. So one oscillation means coming in, stopping, and going out. But over here, I've got it working as a pendulum. Now have a look at how fast how many deflections you get. Okay, so you're getting a lot more for one oscillation. Let me just show you why. I'll stop that if I can. Stop it there. For one oscillation, let's imagine you're starting the pendulum over here. One oscillation, it approaches, reaches the top, goes back over there, approaches again, and then leaves. So you've got approach, depart, approach, depart. So one full oscillation of a pendulum has two lots of approaches and two lots of departures, whereas here, one oscillation is one approach, one departure. So you should get twice as many basically max and mins in there. So I'll just, okay, look, this girl, I've just got this set up with a Handtech digital oscilloscope. Watch what happens when she does just one oscillation. Right, so it's one oscillation. Now you'll notice there it is going in. So it's going into approaching, gets to the top of the solenoid, and the voltage is 0, and then it leaves, goes away, and then it comes back for its return journey. It approaches and then leaves, and you'll notice the voltage is lower. It's slowing down because of air resistance probably, or friction in the nylon cord or something like that. Okay, so that's a neat little one. This is one going just up and down. Right, one oscillation. You see there's just the one peak, max and min peak. Look, I'll get it to do it again. And you can see it's just a bit smaller. Okay, let's move on. Now you can, this is what you can apply it in real life to a guitar. Look, if you pluck a guitar up and down, you get something different if you pluck it longitudinally. I'll just quickly show you, like plucking it perpendicular to the body of the guitar, you'll get one set of frequencies, and if you pluck it transverse, you get another set. I'll show you why. Look, here's basically the coil inside the pickup coil inside an electric guitar. The string is basically a magnet, because you've got a magnet inside the pickup, the pickup coil. So north pole at the top, and what happens is as the magnet comes down and away, it'll induce a current in there. Now over here you can see the difference. If it's coming down, up and down, it's oscillating this way, you get an approach, departure. So one oscillation is one approach, one departure. But if you go sideways, one oscillation is approach, departure, approach, departure. So you're getting twice as many. So this is the setup. I took this to the all the conferences last year, just an electric guitar. Look, I've just got a plug split in two and put it into one of these little J-car preamps. Now they're only $26. They're marvellous little things. And you've got two outputs. So one output I just sent to a speaker so you could hear it. I used a little speaker. I had to carry this around. And then the other one to a Handtech oscilloscope. Now these aren't big. That's probably the size of a deck of playing cards. and this thing is about, probably 4 times that. It's about 15 centimeters across, I guess. And then the output of that straight into a the Handtech program in the oscilloscope. Okay, so let's have a look. Look, I'll pluck it vertically, and you'll notice you're getting 1, 2, 3, 4 peaks across the width of the screen. Okay, let's stop that, and I think she's going to, I get her to pluck it that way. You see you're getting twice as many peaks. Now one is not as strong as the other. You're getting the 4 main peaks, but you're getting twice as many. So that's the second harmonic. So you're getting, with the plucking it up and down, perpendicular, you're getting the first harmonic, and then plucking it sideways, you're getting the first and second harmonics. So it gives a rich sound. Now depending on how you pluck it, you can get various combinations of the first and second harmonics, and that produces the rich sounds of an electric guitar. Okay, oh, here we go. This is just in theory. First harmonic is the blue line, second harmonic twice the frequency. Okay, now lastly, the other prac is suggested is just a transformer prac. Induced EMF from an AC generator. So I'm treating, here's my AC generator. It's just the power supply, the AC, and I've got it going through a air cord solenoid with a steel rod in the middle, and here's another air cord solenoid hooked up to a voltmeter. So a variable voltage goes through this primary coil, and that's reading 10 volts, and the output, the secondary coil, is only producing 2.8. Now the question on the EA is most likely to be something about, if you plug this into a DC power supply, would you get, what readings would you get? Well, you still might get 10 there, but you get nothing, because you need the alternating flux, the varying flux that has to cut from the first coil, cut through the second coil, and it's basically carried through it by the rod. If you just put it up side by side, you don't get much transfer of flux, varying flux. Okay, so you can try this at 2, 4, 6, 8, 10 volts, and you get the output here. Here it is here. The primary, look, 2, 4, 6, 8, 10, 12 volts. The output, look, even at, what's that, about 3 volts in there, you're getting only half a volt out. So the ratio is 4:1. So here we are, 4:1. So 4 volts in, 1 volt out. Terrible efficiency. Ideally, now the syllabus treats all of these coils as being, transformers as being ideal. That's why they have this relationship, saying the number of turns should reflect the ratio of the voltage. But it doesn't, of course. In theory, ideally it would. You might get up to 90%. So 0.9 would be the equivalent of a 0.9, 90% efficient would be considered pretty exceptional. This is, what's that, about 25% efficient. But we can't really talk about that in the syllabus. It's not one of the statements. So you just have to treat it ideally. But for an experiment, you might like to do it. It's only suggested, so students might think, why are we wasting time? The data won't appear on the external exam. But if they're into transformers, there's a heck of a lot going on. And look, I can try different number of cores between them. So there's no core there. Look, 5 volts in, 0.1 of a volt out. Terrible. The core is just a chunk of Rio bar from Bunnings, just a little bit of steel reinforcing rod, concrete reinforcing rod. Single core, 5 volts in, 1 volt out. If you use double core, 5 volts in, 1.6 out. Doesn't improve it much. And you can see here, if you try it at all different voltages, 1 and 2 cores, pretty much the same. You need a different approach to get higher efficiency, but we're not really talking about efficiency here. We're just talking about simple little pracs. Here's one you can do. Look, I've used an IEC laminated steel core, and you just put the two coils on that, and I've just measured the input and output using a oscilloscope. So look, imagine that to be 3 volts in. There's the primary, the secondary is 1 volt out, if you like, and the phase relationship is the same, so they're in phase. So that's a nice little thing you can do, but not a lot to see here. Look, I changed the frequency. I'll just what I did was I used a frequency generator and put different frequencies through this. Now you can see I've got the two voltages the same. Okay, but all of a sudden now this is, look, I should stop it there. That's at about 15,000 hertz. So I've got the frequency turned up to 15,000, and you'll notice the output all of a sudden is starting to increase. Okay, it's a resonance condition, so you're getting a higher voltage out than you're putting in. And if I keep going up to about 25,000, look, I'll stop at about there. Now that's at, whoa, that was at about 25,000 volts. Sorry, 25,000 hertz, somewhere in here, probably about there. Okay, and you're getting lovely increase or resonance. But if you go further, all of a sudden it decreases and it's completely out of phase. So about 30,000 hertz it goes back out of phase. It's not very efficient. So there are maximum minimum frequencies. Oh, sorry, there's a resonance point where you're getting maximum transfer of voltage at least. Of course, increase in volts, the current would go down. I mean, you can't get more power out than you put in, but you can certainly get more volts out than you put in. Okay, I'm going to leave that there, and that's it. So thank you for that. Might leave it there, and you can find this on, or you probably have found it on the YouTube. But there's other ones I'm going to make for 2018 and 17 and so on. I'll get around to doing the voiceovers. That's it.